Welcome back to the PMDK Developer Day. Our next talk is on endurance benefits with persistent memory. Sergey, please take it away.
Thank you, Usha. Hello, everyone. I'm Sergey Vinogradov. I'm software development engineer from Intel. I have been working more than 4 years on the persistent memory software ecosystem, and today I'm going to talk with you about endurance and what benefits persistent memory can bring to your applications. So here's the agenda of this talk. So I will do a quick introduction and briefly discuss with you endurance characteristics usually applied to the storage devices, and we will compare it with persistent memory endurance with some SSD endurance. And then we will talk about the software part, and especially about write amplification we usually have in software, which give us a great impact to the endurance and sometimes impact the lifespan of our storage devices. And then we will discuss how software can be modified to efficiently use persistent memory from the endurance perspective. And we'll do a conclusion at the end. So let's proceed. So this is a picture we usually show when we introduce persistent memory. So we are showing that persistent memory fills the gap in the memory hierarchy and took a place between DRAM and SSDs. So it's something in the middle between memory and storage hierarchy. And as Piotr and Andy introduced it in their talk, so persistent memory, it's a new kind of device which combines characteristics of memory and storage. So it's byte addressable like memory, and can be accessed directly by CPU using load and store instructions. It has cache line granularity access, but also like a storage, it's a persistent, and it's the data stored in a persistent memory can survive process restarts. And it means that persistent memory can be compared with regular memory, with DRAM, and usually we compare the cost and performance. So we know that the performance of persistent memory is a little bit slower, so it has higher latencies and less bandwidth, but the cost per gigabyte is lower comparing to DRAM. And comparing to SSD, we also do a comparison from the perspective of performance, and we know that persistent memory is faster than SSDs. It has significantly better latencies. But today I'm going to discuss with you the advantages of persistent memory from the endurance point of view. And we'll see how persistent memory can help in your setup, in your applications. And on this slide, I decided I just pick some Intel SSD and decided to compare its characteristics with obtained persistent memory device. So I took 128 DIMM, 128 gigabytes DIMM, and compare it with Intel NAND SSD for data centers. The model is P4610, and the capacity is 3.2 terabytes. But I just did it for a quick exercise, and as a homework, you can choose another model and find the spec on Intel website and do a comparison by yourself for the model you are interested about, right? But yeah, I just did this comparison for illustration. So usually when we talk about endurance, so endurance describe it using two characteristics which can be calculated one from each other. So the first one is endurance, and usually it's exposed as a amount of petabytes can be written to the device before it's wear out. I hope you know that lifespan of a storage device is limited by the number of writes we can do to this device. So, for example, for NAND SSD, so usually when you do write, so you need to erase some block and then reprogram this block again to write new data. And usually we are working with the block storage device using, for example, pages, and usually it's a 4 kilobyte block. So it means that when we need to update some data, we need to update the full block. Even we need to update just a few bytes in this block. So anyway, so endurance is the first characteristic, and the second one, it's a DWPD, so it's disk writes per day. So these characteristics can be calculated from the endurance. So we just need to know the capacity and the warranty period. So, and disk writes per day tell us how many times we can fully rewrite the storage device per day, right? So for this particular example, for example, the endurance for SSD, it's 21.85 petabytes. So we need to divide this to the capacity and to the warranty period, to the 5 years and to 365 days. Then we will receive a disk writes per day. And it means how many times per day we can rewrite this SSD to support the full warranty period until we're out. And for obtained persistent memory, if you will look into the specification, you will see that we have two values for endurance. And these two values provided for two cases. So the first case, when we do writes by the chunks of just 64 bytes, it's just a cache line size, right? And in this case, the endurance is 91 petabytes. But it's much more efficient if you will do writes by the chunks of 256 bytes. In that case, endurance is much more higher, and as you can see, disk writes per day is different for two different chunks. And comparing to SSD devices, when we are using a block size as a grain size, right? It's much more, so for persistent memory, the grain size is much more lower comparing to SSD. We can do a fine grain updates, which also impact lifespan of the SSD. And on the last row, I tried to calculate the maximum possible write rate that the storage device can support to to be in a good condition for the full warranty period. So, and as you can see, SSD can support much more less traffic, write traffic, comparing to persistent memory devices. And also I tried to illustrate it on the diagram on the right side. So I just tried to show you the dependency, so lifespan from the write rate. So, and as you can see, for example, if the write rate is too high, so persistent memory can support it and survives better on write-intensive workloads compared to NAND SSD. What does it mean for us? So it means that write-intensive workloads can benefit from persistent memory because, for example, we can save money, because when storage device wear out, we need to replace it with a new one, and we need to spend money for this. And this is one of the advantage comparing to performance. In addition to performance, it's endurance characteristics of persistent memory. So just if you have any write-intensive workloads, you can monitor, and if you have a problem with the lifespan of your storage device, you might consider persistent memory for you. Then I'm going to talk with you about write amplification, because write amplification, it's a situation in our applications which significantly impacts lifespan of our storage device. And to talk more about that, so as a first step, I just would like to introduce the terms for our discussion. So there are actually two major sources of write amplification. So the first one, it's a software. So we might have a write amplification on a software layer, and the second source, it's a hardware layer. And to illustrate this, I just prepare a simple picture above. And so just to briefly describe what is write amplification. So let's imagine we have some user application, and this application needs to store some amount of information to the storage device. So usually we are using some framework, so it might be created by ourselves, or we might use for third party. For example, I just provided, for example, a well-known RocksDB and LevelDB. It's well-known key-value storages. And also I put there PMDK as an alternative because it's, as Piotr mentioned in his presentation, it's developed for persistent memory, but it's also used to store key value pairs in a persistent domain. So, and write amplification happens when user application want to store some amount of bytes, but internally storage framework might do some transformation. So we might do fine-grain changes which lower than the granularity size of device. For example, for SSDs, it's a block size, which is usually significantly bigger than the cache line size. For PMDK, since it's developed for persistent memory, the grain size is just a cache line, but let's imagine we need to update just 1 byte. In that case, when we update in just the 1 byte, the full cache line is sent to the storage device, and we might say that the write amplification, software write amplification, it's 64, right? So, and on the right bottom kernel, I just provided formulas to calculate, to simplify calculation of write amplification. So software write amplification can be defined as a ratio between amount of bytes we send to the storage and amount of bytes application wants to store. So usually amount of bytes sent to the storage exceeds the number of bytes application wants to store. It's a software write amplification. Then when the data came to the storage device, so media controller which resides on the storage device just need to do some work to put this data on the media, right? And firmware or controller logic might introduce hardware write amplification. This is the source of the hardware write amplification. And for example, for NAND SSD, as I mentioned before, to do any write, we need first erase some block and reprogram it again with the new data. And the size of block might exceed the actual amount of information you would like to write. And this is the source of the hardware write amplification. So, and the total write amplification, it's just a multiplication of the software write amplification and hardware write amplification. So, pretty simple. During my talk, I will mostly talk about the software parts because we are software developers, and when the hardware is released, so we have no much choices to impact hardware write amplification. We might only optimize the software. So the very good example of a software write amplification. It's a log structured merge tree. It's a very popular data structure developed for block storage device, and it's optimized for writes, and it allows you to organize a key-value storage on SSD or on hard drives, and it's optimized for this kind of device. So usually key-value storage workloads, it has a random access pattern. So we just randomly insert keys and randomly accessing value by keys. But LSM3 allows you to get sequential access to the storage device from the random access to the framework. It's a very interesting idea of LSM3. And to understand the software write amplification, I will just briefly describe you the algorithm itself. So usually LSM3 consists of the two major parts. So the first part, it's a mem table. It's stored on DRAM, and it works as a hot cache. It contains the recently used data. And the second big part, it's sorted string tables, which is a files on the file system. And so the storage layer consists of different levels, which is used for compaction. So just to illustrate how it works. So imagine we have a new entry we would like to insert into our key value store. So initially this value inserted to the mem table, and it's put it to the log. It's just append only log file, which also resides on the file system, and it stands for durability. So in case you have a crash, or in case you need to restart your application, so to restore data stored in mem table, this log file is used. So when we put the new entry to the mem table and writing it to the log, this is the first time we write this entry to the file system. Then during the work, when mem table size achieves some threshold, we need to flush the content of mem table to the file system. We need to flush it to the SST file. And this procedure, call it compaction. It's pretty easy to understand, so we just need to merge content of mem table with the content already stored on the level 0 of SST tables. So at this moment, we write our entry the second time. So we already have a write amplification equal to. But usually for optimizations, the storage part consists of multiple levels. For example, in RocksDB, you might have up to 6 levels, as I remember. And each layer just is bigger than the previous one. And so when we achieve some threshold on the level 0, for example, we are compacting entries from level 0 to level 1, and so on. So as you can understand, each entry inserted to LSM3 it participates in compaction several times. It means that it's rewritten several times and moved from file to file. And this is the main source of write amplification. So while LSM3 optimizes it for writes, and actually it transforms random access to key value storage to the sequential access, sequential writes to the storage device, it's good for performance perspective, but from the endurance perspective, it's not very friendly. So compaction actually causes software write amplification. And for LSM3, we can define the software write amplification as a ratio between bytes written to the disk, so the amount of writes we do to SST tables and to the log file, and amount of bytes we put to mem table. This is the software write amplification for LSM3. And even in theory, it might be very high, right? And it impacts endurance significantly on a software layer. And remember that there is additional amplification on a hardware level. And then the question is how persistent memory might change the situation, because persistent memory might be considered as an alternative. Yeah, as an alternative for for the storage device. To answer this question, we decided to compare existing software solution designed for the storage devices based on LSM3 algorithm with PMDK, which is designed for and optimized for persistent memory. And during this comparison, we might get an answer. Does software designed specifically for persistent memory can bring us any benefits from the endurance perspective? So for this experiment, we took RocksDB and LevelDB as a famous and popular examples of LSM3-based frameworks and PMDK. So I will briefly talk about PMDK components on future slides. So in our experiments, we just selected 3 write-intensive benchmarks. It's field sequential, field random, and overwrite. So field sequential just insert new entries to the empty database in a sequential order. So field random benchmarks do almost the same, but it's insert new entries in random order to the empty storage. And overwrites, it works with pre-filled storage, and it just randomly rewrites existing entries in a database. And fortunately, PMDK, RocksDB, and LevelDB use the same benchmarking tool. So when we designed PMDK, we decided to port dbbench. It's a benchmarking tool used by RocksDB and LevelDB just to simplify comparison, to simplify performance comparison of PMDK versus RocksDB and versus LevelDB. But fortunately, we can also use it to measure endurance benefits. So in our cases, we run RocksDB and LevelDB to store data on a persistent memory. And RocksDB and LevelDB, so we run it without any modifications, and they are using persistent memory as a block storage device. So we are calling this mode storage over updirect. So because on persistent memory we have a DAX file system, and we can use a regular file API, file read-write API, and that's it. So it means that your existing software can benefit from the persistent memory out of the box. While PMDK use persistent memory in updirect mode, which means that we avoid page caching and we directly do updates from CPU to persistent memory using just load store instructions. So so we did experiments for 3 different dataset sizes just to investigate if it depends on the working set size. So we choose 10 million entries, 20 million entries, and 30 million entries. So, but now when we choose a benchmark, the question is how to measure software write amplification. It's pretty easy to understand it, to understand the formula, but how to measure it? So we need to know the amount of bytes application want to store, and the amount of bytes the application actually sends to persistent memory device, right? And we use the following. So dbbench already reports the row size, which is the cumulative size of entries inserted by the benchmark. So imagine if we have a size of entry just 1 byte, and we have 1,000 entries, then the cumulative size, the row size, would be 1,000 bytes. That's it. This is the amount of bytes application would want to store. And to monitor and to calculate the amount of bytes the application actually sent to device, we are using PMU counters. So PMU is a processor monitoring unit available on the Intel CPUs, and it provides a lot of events which is suitable for different to monitor different conditions. And for this experiment, we found 2 useful events. It's encore events that measure number of cache lines which were sent to persistent memory device. So it doesn't matter which events to use because our experiments shows that both events report the same values. So in our experiments, we used the first one. And we captured it using Emon tool. It's a command line, very simple command line tool distributed together with Intel vTune Profiler. So you might find the executable when you install the vTune. You might find the Emon executable, which allows you to capture any events, any PMU events in accounting mode. That's it. But if you're an expert in perf and you would like to do experiment by yourself, you can use perf for this purpose. You just need to know the event code for these events, and that's it. And we define a software write amplification for our experiment as a ratio between amount of data written to PMM measured by anchor counters and the row size, which is the number of entries multiplied by the size of one entry. So that's it, pretty simple. Now let's look to our results. So as I mentioned before, we provide the results for 3 different dataset sizes. So this is the first one, 10 million entries, and the row size in that case. So in our case, each entry has a key size 16 bytes and value size is 800 bytes. So, and for this case, the row size is about 8 gigabytes. For 20 million entries, it's twice more. So it's the row size it's about 15.5 gigabytes. And for 40 million entries, the row size is 31 gigabytes. So, and as I mentioned, there are 3 benchmarks: few sequential, override, and few random. And here is the amount of bytes which actually written to persistent memory device. So we measured it using anchor counters I mentioned before, and we measured it for PMMKV, RocksDB, and LevelDB. And with both, I just highlighted the write amplification, software write amplification for PMMKV, for RocksDB, and for LevelDB. And as you can see, the write amplification on a few sequential benchmark, it's just a little bit better for PMMKV, a little bit lower comparing to RocksDB and LevelDB. But it happens because RocksDB and LevelDB benchmarks optimize it for few sequential, and they just avoid any compaction when they run benchmark and do compaction after benchmark completed. So that's it. But override and few random is a very representative benchmarks because I believe it's much more closer to the real life comparing to the few sequential. And for these benchmarks, we can see significant difference between PMMKV and RocksDB. Again, all frameworks use persistent memory as a storage device, but PMMKV use it as a in updirect mode, and so we are using PMDK to interact with persistent memory, and we employ fine-grained accesses, while RocksDB and LevelDB use persistent memory just as a block storage device. And here you can see the difference. So, and for different working set sizes, we can see that results for PMMKV is pretty consistent. While for RocksDB, it's vary for different dataset sizes, and for LevelDB, it's there is not so much difference, but still we see some difference, for example, between this one and this one. And just to illustrate the overhead of, overhead in terms of writes, right, of PMDK transactions. So you asked the question to Piotr, what's the overhead of transactions? And this experiments just confirm that, so in PMDK transaction, we need to make a copy, right? And if you look into override benchmark, which just update existing items in a key value storage. So the write amplification, it's 2.5, right? But theoretical write amplification, so should be around 2 because we need to open transaction, copy old value to undo log, modify existing data, and then submit transaction. The real write amplification just a little bit higher comparing to the theoretical one, but I believe it's pretty good illustration of the theory. So once we get this data, the next question is what we can do with existing software, right? Because we have a lot of legacy software created for the block storage devices, for SSD, for hard drives. So, and I have several answers. So the first and obvious answer, so we can just run any existing software on a persistent memory and use persistent memory just as a storage device, as a regular storage device. Of course, it's not an optimal way, but you still have some performance gain, some endurance gain, because just the hardware characteristics of persistent memory is better compared to SSDs, right? It has better performance, it has better endurance. So running any existing software out of the box, you already have gain. And on write-intensive workloads, you might save the life of your SSDs, of your storage devices, and it means you are saving money if you will add persistent memory to your storage hierarchy. The next thing you can do, I'm just showing how you can modify LSM3 algorithms. So PMDK provides, as Piotr mentioned in his presentation, PMDK provides various set of libraries for different use cases, and fortunately, it already has a persistent memory resident log file implementation. So there is a libpmlog library which is designed specifically for persistent memory, and it works as a append-only log. And it's optimized for fine-grained access, optimized for persistent memory. And so the easiest thing you can do in your, for example, in LSM algorithm, you can just replace the log file with pmlog file. And all changes in memtable can be tracked in persistent memory. So this is the easiest modification you can do in your software, and it looks pretty simple because you just need to replace one simple component, right? But the write amplification still would be high because you still have a storage layer. You still need to do a compaction because the capacity of persistent memory is lower than SSD. You still need to flush your data to SSDs. So, but you might have performance improvements because latencies and bandwidth characteristics of libpmlog should be better because it directly works with persistent memory, while existing solution for logging just use a file system. They should go through the system API, from the syscalls, and so on. So with these code modifications, you might have a performance gain. So the next thing you can do, so you can completely replace your existing key-value storage with PMKV. So PMKV, as Piotr mentioned, so it's a key-value storage specifically designed for persistent memory. So just to quickly introduce what it is, so PMKV, it's written in C++, and internally it has some created some native engines dedicated for different use cases. So we have engines for persistent use case, we have engines for volatile use case when persistent memory uses it as huge capacity. But all of these engines have the same API which can be used in your application. So we provide C++ API, and we provide various bindings to to the higher level languages. So we provide bindings for JavaScript, for Java application, for Python, and so on. And of course, PMKV optimized for persistent memory. But as I mentioned before, so persistent memory has a lower capacity compared to SSD. And so another possible solution is a hybrid solution when you can combine all hardware available to you. For example, you can put memtable on DRAM and it will act as a fast hot cache. And so accessing data from DRAM provides best performance comparing to persistent memory, comparing to SSD. Then we might use libpmlock and libpmkv just as an intermediate layer before SSD, just to accumulate write traffic, right? Because libpmkv optimized for fine-grained access. It allows you to decrease software write amplification because we're just updating the data in the persistent memory with cache line granularity. And on the lower layer, we still can use SSDs just for capacity because SSD provides bigger capacity comparing to DRAM, comparing to persistent memory. So that might be the choice. So in these 4 slides, I just tried to summarize what you can do to utilize persistent memory in your storage applications. So actually, I'm almost done with my presentation. Just to summarize, so persistent memory is new kind of device which can be used as a new layer in a storage hierarchy. Out of the box, it provides better endurance comparing to NAND SSD. It provides better performance, but you also might want to optimize your application to achieve higher benefits. And PMDK so can be used as building blocks to change your software because you should not create everything by yourself. So in PMDK, we already tried to address some basic usage models, and you might look into what PMDK can provide to you and just use it in your applications. And as I mentioned before, the main advantage from the endurance perspective, you might decrease the TCO because if you have a workloads which cause your SSD to wear out quickly and faster than the warranty period, you might consider to use persistent memory to accumulate write traffic. So you might use persistent memory out of the box, just running your application as is, but again, to achieve best performance and best endurance characteristics, you might want to optimize your software for persistent memory, and PMDK should be your choice. So if you still have any questions or feedback, you can send it to me, or you can visit the pm.io site, and there is a links where you can post your questions. So that's it. So I'm ready to answer your question.
All right. Thank you so much, Sergey. That was a great presentation. So we have a few questions coming from the audience. Is there a use case where persistent memory will not perform as good as SSD?
Yeah. So I forget to mention on my slide that in our experiments, we run RocksDB and LevelDB with eventually consistency mode. So it means that RocksDB and LevelDB in our benchmarks perceives the data not on every insert operation. So it means that they provide eventual consistency. So it means that in case of crash, when the data would be restored, it would be restored to some state in the past, not to the recent one. It might be the case. While in PMKV, we only support strict fault tolerance. And but the price for that, it's a performance, right? And sometimes PMKV performance might be not as good as RocksDB, but you should understand that in PMKV we support strict consistency, while in RocksDB and LevelDB by default they support only eventual consistency, and they are multi-layered software, and they're using DRAM caching, and DRAM is faster than persistent memory. So to achieve best performance, and for apple-to-apples comparison, so we should build hybrid solutions for persistent memory where DRAM will be used as a hot cache. So my simple answer, so when you compare in performance, just to make sure that you do apple-to-apple comparison.
Makes sense. Yeah. Thank you. The other question is, how can I tell how worn out my persistent memory module is?
So sorry, can you repeat?
How can I tell how worn out my persistent memory module? Are there any tools to basically figure that out?
So you mean for configuration? I think there is a tool called NDCTL.
That's
right?
And,
yeah, it's open source tool, and I believe you also can comment on
yes.
this. On this
so NDCTL is an open source Linux-based configuration tool that also has options to look at, different ways like monitor what's going on the DIMM, as well as look at how worn out the DIMM is as well from the endurance perspective. So in our final list of resources that you can go back to, we have a link to our user guide for NDCTL, basically docs.pm.io, and it has you can look at different options to figure that out, and we have a really good user guide available there. The next question, do you think the techniques you described in LSM3 and the ones found in PMKV can be combined to achieve lower write amplification?
I think so, yeah. As I mentioned on my slide, so we have different choices how to enable software for persistent memory. So the easiest choice is just to use it as is out of the box, right? But to achieve best performance, best endurance, I believe software modifications is required. And yeah, in ideal case, we should consider hybrid solution, and we should utilize DRAM, persistent memory, and SSD simultaneously to gain benefits from each of type of these devices. This is my answer. And while I showing the LSM3 just for comparison, actually I believe it could be applied to any other storage applications. So the thing you should just do, you should somehow measure write amplification in your software for SSD. So usually the good indicator that if the lifespan of your SSD in your data centers is lower than the warranty period, then it's a good indicator to consider persistent memory from the endurance perspective.
Thank you. Can you also, so how can I measure write amplification from my application? Is there a way to do that?
So yeah, so actually I just showed it on my slide. Let me show it again. This is the methodology we use it in our experiments. So as I mentioned before, I run all benchmarks on a persistent memory, right? And there is a hardware counter in Intel CPU which allows you to count the number of cache lines in your persistent memory application, right? So this is the first counter, and this is the second one. It's just two different counters from two different subsystems, but they actually count the same event. So they count the number of cache lines sent to PMM. But if you have no persistent memory in your lab, there is also PMU events that allows you to measure write traffic to SSD device, to NVMe SSD device which connected through PCI. So if you need this information, please connect me, and I will tell you how which counter can be used to measure the traffic to SSD. So if you have SSD only system, it's also possible to monitor the amount of bytes you have sent to SSD, to NVMe SSD.
Great. That's the last question I had. I don't, so let me check the Q&A window one more time. I don't see any other questions coming up. Just a reminder that all the presentations are recorded, and we will have we'll provide you access to the recordings and the slide after the event. So just if you have any questions, so you know how to get back to us with the questions. So because we don't have any other questions coming in, let's take another short break, and we'll come back, and we'll have Igor talk about the concurrency in failure atomic data structures.